Today's colloquium speaker, Paul Steinheart, is I have to look at my crib notes, the Albert Einstein Professor in Science at Princeton, the director of the Princeton Center for Theoretical Science, and one of the world's foremost cosmologists. Paul has published more than 200 papers, along with 6 patents, numerous popular articles, and the book Endless Universe, which he co-wrote with Neil Turok. Paul's honors include the PAM Dirac Medal for his contributions to the development of the inflationary model of the universe. His interests range beyond cosmology back to Earth and geology, and that has made him a co-discoverer of the first quasi-crystal, which is a rock that skeptics had long argued could not exist. Paul received his bachelor's degree in physics from Caltech and his master's and PhD degrees in physics from Harvard. He taught at Penn from 1981 to 1998, when he took up his position here at Princeton, where he is on the faculty of both the departments of physics and the Department of Astrophysical Sciences. We're extremely happy to have Paul here today, and please give him a welcome.
Today, which has to do with what happened in the universe 13.7 billion years ago. In particular, I want to talk about 2 competing ideas about the origin, evolution, and future of the universe, one of which is based on the idea that what happened 13.7 billion years ago was a Big Bang. Literally, the creation of the universe, space, time, matter, and energy from nothing into suddenly something, a space-time filled with hot matter and radiation that expanded and cooled over the next 13.7 billion years. So according to this picture, the entire history of the universe involves events that occurred just over that period. That is the current consensus view. And I want to contrast that with an alternative view, which is based on the idea that instead what happened 13.7 billion years ago is not a Big Bang, but a big bounce. A bounce from a previous epoch of, you can think of it as contraction, which then led to a bounce and then re-expansion again. So that, in this case, the key events that set up the large-scale structure of the universe actually occurred before the bounce, or you might, if you like to think about it that way, before the bang. So these are 2 very different histories of the universe. The debate that's happening now concerning these 2 different views of the universe is critical to our understanding of cosmology and to fundamental physics. And I'll try to argue that the debate is also critical to our view of science generally, because at issue will be questions like, what are the bounds of normal science in terms of explaining why the universe is the way it is? So they both agree that the stuff that makes up you and me, ordinary matter, stuff that's made of atoms or pieces of atoms, electrons, protons, neutrons, etc., only occupies a small sliver of the total energy budget of the universe, less than 5%. As I said, it's remarkably fast. The acceleration is exponentially greater. In the current universe, the universe is speeding up, and it's going to stretch by a factor of 2 now and going to the future roughly every 10 billion years or so. So 10 billion years for a doubling time. For this inflation, we want the doubling time to be 10 to the minus 35th seconds, because we need to accomplish this smoothing really, really fast before even a minute has passed. So we need this to be fast. And we don't, unlike today's dark energy, which we don't know if it's going to be around forever or not, this inflationary energy better for sure last for only a short period of time, because we also want to finish within a fraction of a minute. So, for example, in typical models, it might last only 10 to the minus 30 seconds. So this whole big deal about inflation is only talking about a brief instant around 10 to the minus 30 seconds. So in that sense, it seems rather trivial. But what happens in that 10 to the minus 30 seconds is amazing. The universe, if you compare 10 to the minus 35 to 10 to the minus 30, that's a factor of 100,000. It's undergone 100,000 doublings. That's, taking a region, say, the size of an atomic nucleus and stretching it to a size which is unimaginably, exponentially greater than the horizon we observe today of 14 billion light years. Which means that the patch of the universe we observe today was, before inflation, much, much tinier than an atomic nucleus. And as far as we've been able to measure so far, it's in beautiful accord with observations. Well, That's at least the story that would be told in lots of journals and newspaper articles. The question we want to raise today is this really true? Is this really the way the model works? And if the answer were yes, I probably wouldn't be here giving this talk. So it's going to turn out that the answer is actually no, this actually isn't the way inflation works. And we've actually known this for more than 30 years, but we haven't exactly made it widely known. So this is a serious problem. We don't, the natural initial conditions, or the naive, I should say, the naive initial conditions you expect to get out of the Big Bang are not give you much of a chance of inflation. Somehow something special has to have taken place. And there is no theory at present to explain what that special thing would be. So this is an open issue. But even more serious is the issue of prediction. Does this theory, even if I give you that patch to begin with, does it really produce all the nice outcomes that I described to you? And the answer to that is also not so simple. So in fact, what really comes out is the story is literally anything will happen, can happen, will happen, and will happen an infinite number of times if I look over this spectrum of pockets. So a theory that was supposed to be predictive and explain why our observable universe is the way it is, has in fact produced something that's called a multiverse. Welcome to the multiverse. A multiverse in which anything that can happen will happen and will happen an infinite number of times. So if you ask what inflation predicts, this is the one thing I'm confident that it predicts. Anything. Now, this is an unmitigated disaster, at least from my perspective. The universe has produced everything rather than the particular thing we wanted, and it's predicted nothing. What was supposed to be a theory to explain why the universe is the way it is has become a theory of anything. Anything goes. So what do you do about it? Well, hold it, you say. Hold it. Hadn't you read newspaper articles, even recently, let's say when the Planck satellite experiment announced its results in March, that said that the data agreed with inflation? How does that comport with what I just said, that inflation would allow anything? Anything they would have observed would have been equally good. So how do those two things fit with one another? Am I lying to you? No, I'm not lying to you. What's happening when you hear those claims in the newspaper is what they're doing is that they are imagining what inflation would produce if there were not eternal inflation. Before eternal inflation was discovered in 1983, we thought we knew what inflation produced. We ignored the rare fluctuations, just cut them out as if they never would exist, and made predictions. When they say it agrees, what they mean, what they should make very careful to say is, provided that we just blind ourselves to the fact that there's eternal inflation. There's going to be these rare fluctuations that give us eternal inflation. If we imagine that doesn't happen, even though we have no reason for that not to happen, then the data agrees with inflation. And I really wish they would say something like that, because I think it really confuses the story not to make it clear that that's what you're doing when you're saying it agrees with the data. Because it gives you much more confidence that we've tested a model when we really haven't. When the theory really isn't that predictive. Since, again, anything they would have observed would be, if it's physically possible, it should be possible in the multiverse. Of course, you shouldn't be satisfied with such a theory, and neither are theorists. Quietly, many of us have tried to fix the problem. And many ideas have been tried. One of the ideas is to add something to the theory. You're going to have to add something beyond what the theory gave us, because as far as it goes so far, it's just giving us everything. So one of the ideas is to introduce the idea of what's called a measure principle. Of course, the moment you introduce this measure concept, you're already admitting that you have a problem with inflation alone. You're already admitting that what inflation gave you is not what you wanted, but everything. So that's why you're introducing the measure. But people have gone through a set of measures, and no one has found a measure which is convincing. This has then led to the idea of, well, maybe we should turn to something beyond the usual bounds of normal science, the concept of anthropic reasoning. So anthropic reasoning is essentially using the fact of our existence to help select from your model regions in which you're likely to find humans. So you're assuming the existence of humans and then trying to explain why humans find themselves in the situation in which they exist. There's a reason why it's not called scientific reasoning. because it really lies beyond the boundaries of normal scientific reasoning. But even so, let's just follow it for a moment and see where it leads us. Now, I believe, well, let me wait a second before I say that. Yeah, I believe that a difference of 1 second does not make the difference in whether sentient beings like us can exist. I think we could. So there's no reason why we couldn't live in a younger pocket. That would be exponentially more probable. So this anthropic reasoning also doesn't really take you, even if you go beyond the bounds of science, doesn't really take you where you want to go. And then the literature keeps continuing. You'll find lots and lots of articles combining anthropic reasonings with various measures and the like. And as I said, so far nothing has succeeded. And at this point, some people have said, some prominent people have said, well, maybe we should just lower expectations for a theory. Maybe it's good enough if what inflation does is produce a universe where at least there's some pockets in which we can exist, and just settle for that, without explaining why we live in that pocket rather than something else. Well, I think this is a very important issue, not just for cosmology, but for science generally. When we begin to introduce anthropic reasoning or lowering of expectations into our views of where cosmology could lead us, we are bringing an end to what I would call normal science. We're saying there's a limit to how far normal scientific reasoning can take us in explaining why the universe is the way it is. Even though we observe the universe to be extraordinarily simple and uniform, nevertheless, we're being driven by this inflationary idea to ideas that go beyond these bounds. Is that the direction in which cosmology and science has to go? Or is it time to rethink? That's the issue that's on the table. So what would rethinking mean? Rethinking would mean you got to go back to square one and look at the assumptions you made that got you into this mess, if you think it's a mess, and change something. Yes?
Does the theory require for the universe to be cyclical, or can we go back to bring back Fred Hoyle into the picture, a steady state situation where it actually contracts, and then there's an expansion, it's a one-time thing?
So you have lots of degrees of freedom. So I think you should think about it there's being lots of ways in which you could go with the basic idea of bouncing. It could be a one-time bounce idea, but then you could. But Hoyle's idea was not what we call geodesically complete. If I trace it back in time, I'd find there'd be a question of what happened before. It would require more and more special conditions the farther back I trace it back in time. So it's not a particularly appealing theory. He wasn't trying to ask the same questions we try to ask today. He had different goals in mind. But if you were to take that theory and say, could that explain, for example, why the universe is uniform and flat? No, it's not. His model is not a particularly good one for that purpose.
No, but I'm asking if we take some sort of a steady state.
But you could have.
Slowly.
But before this, but you began. Before your first slowly, I'm going to ask you what happened before then. For physics, you're going to have to tell me, did it contract from infinity or something like that? And is that geodesically complete? It turns out not to be geodesically complete. You need to explain more than that. So, but you do have freedom. It doesn't have, for example, in the cyclic model, we're saying, well, the bounces, the cycles are more or less the same on average. It didn't have to be that way. You can invent physics where every bounce would produce something different. You'd have much less control, much less predictive power in the theory, but you could at least explain the conditions in our current cycle. So you're opening up the realm of possibility. I think the interesting thing at the moment is to see how far you can push the tightest, most constrained version of this idea, which is what the cyclical model is. That's why I'm pursuing it. If it breaks, then we'll have to think about other things. Yeah?